Okay, I want to start out this short video here by discussing the what's called the topology of the plane. Okay, I'm going to start here. S is some subset of the plane. Okay, that's all I've said right here. S is some subset of the Cartesian plane here. Here's some definitions here. P, that's a point. P is an interior point of the set S if there exists an open disk D centered at P that is entirely contained in S. Okay? So for example here when I'm drawing this, with this particular picture, my set S, it has this little boundary here. Can you see it? Okay, this solid line. Okay, I've got an open dot right there. I've got a solid enclosed dot here. This boundary up here is actually dashed. And then I did what? I've shaded the inside here. Okay, just to help you understand my picture here. In this particular drawing here, I've got P in here. See where P is right now? Okay, so this is my initial P right there. Okay, you can see. That point P is an interior point to the set S because you see what I can do? I can actually center a little open disk at P and have that entire open disk contained within S. Okay? So that point P must be an interior point to S by definition. Okay? Okay, so I've got that statement written here. P is an interior point. Okay, how about Q up here? Q is up here on what we would call the boundary, and I'll explain more formally what the boundary means here in a second here. But just use your intuition right here. It's up here on this dashed curve, okay, on the boundary curve up here, Q, all right? This is what we would call a boundary point because of the following here. If I take any open disk, no matter how small, centered at Q, it is not true that that disk will be entirely contained in S. Do you see that? It'll always contain points in the complement of S, or in other words, outside of S in the real plane. Okay? By the way, that's exactly the definition of a boundary point. A boundary point has the quality that every open disk centered at that point contain points of the set, when in this case S, and its complement, all the elements that are not in S but are still in the plane. Okay, Q is clearly not interior. It is in fact what we call a boundary point by that definition. Here I've got R out here. This is called an exterior point. It's exterior to S. It's not a boundary point, and it's certainly not an interior point, because you could imagine what? A sufficiently small open disk, right? Centered. Remember, an open disk includes the interior of that disk too. There I am using words in two ways. Not really. They mean the same thing. Here, I'm continuing everything inside that open disk, okay? You see, this open disk has nothing whatsoever in common with S. It doesn't overlap S at all. R is what we then call an exterior point, okay? So the points come in three different kinds. They could be what? Interior points. They could be exterior points, or they could be boundary points, depending on the set that you're looking at. Okay? So that's just a quick definition here. We're going to use that here in a minute in defining some more facts about sets here. Okay, I call this lecture 28, though it may not be. Anyway, let's continue with our discussion of the topology of the plane here. Okay, this is a following definition here. A set S of the plane is open if every point of S is an interior point. Okay, if every point is an interior point. Here's what I've drawn here for you. So see, I have kind of a dashed boundary here. Okay, and I've got a dashed boundary here. And I'm considering my set S to be everything inside that, so that's what that shading is, okay? So imagine everything inside here. I claim that this is open, okay? Why is it open? Every point is an interior point. Now remember, when I draw the dashed line up here, or the dashed curve, I should say, remember that's not actually part of the set, right? It's not part of the set. It's the boundary of the set, but it's not part of the set. Okay, so I'm not interested in those points at all here. They're not part of the set S. But take any point in S, okay, let's say I've got a point there I'm making red. Is it clear from the formation of this set that I can do what? Take a sufficiently small open disk. It's got to be open here, so don't include the boundaries. Open disk centered at that point. That's what? Every point in that open disk is contained inside S, okay? I can definitely do it, okay? So this is an open set, okay? This set is not open, okay? Why isn't this set open? Well, do you see it includes its boundaries? So suppose I take, these are interior points, okay? That's cool. So that set has some interior points, that's fine. But not every point of the set is interior point. Remember, every point of the set has to be an interior point here. See, if it includes its boundary, unfortunately, here. So right here, see, if I took a point right there, it is simply not true that that's an interior point. Why? Well, it's not true that, I mean, I can find, in fact, every open disk centered at that point, what? Contains points that are not contained inside S, right? No matter how small I make that open disk centered at that point here, or any point on the boundary, there's points that it won't be contained in S here. So this point S, or this set S, contains points that are not interior points. It is not open. Okay, it's not an open set. By the way, let's throw this in here. The empty set, sometimes written this way, the null set, has no points at all, is considered open because the definition is vacuously, you can't read this at all, vacuously satisfied. What does that mean? That means the set of interior points would be empty because there are no points, and we consider the empty set a subset of the empty set, you see. Okay, so it does contain all of its own interior points. All right, if you don't like that definition, just, okay, we'll throw in the empty set is also an open set. Okay, let's go to another definition here. A set S of the plane is closed if it contains all of its boundary points. Okay, so this, like my previous example, that's actually what we would call a closed set. Okay, it contains all of its boundary points. Remember what a boundary point was? A boundary point was what? A point of the set such that what? Every open disk centered there at that point is going to do what? It's going to contain, remember, an open disk looks like this. It's a boundary that's open. Okay, so a dashed boundary, an open disk also, but it includes the interior. Okay, so if I have an open disk here, imagine that guy centered at a point on the boundary, or at a point there. It contains all of its own boundary points. Does that make sense? This is a boundary point, right? That's a boundary point that I have right there. That is part of the set also. Okay, that is part of the set. So what? And that's true for every single boundary point. Okay, now this set has points that are not boundary points. It has interior points, but that's okay. All I'm saying is what? It's closed if it contains all of its own boundary points. Okay, if it contains all of its own boundary points. This does. Okay, this one is also closed. Notice these solid curves here. These are solid. That means they're being included. This is closed. Okay, what are the boundary points for this set? Okay, what is the boundary points for this set? Every open set contains points what? Every open disk centered there contains points in the set, right? namely itself, and what? Points outside the set. So the boundary of that set is that point itself. Okay? The empty set will also be considered closed, okay, in a vacuous sense. Okay, it doesn't have any boundary points. And the empty set is considered a subset of every set. So, okay, this is an exercise for you. Okay, so EFY. The entire plane is both open and closed. Can you prove that? Okay. The entire plane is both open and closed. Okay. The empty set is both open and closed. Okay, but there's no other such sets. Let's take this set here. Okay, do you see what I've done here? I've got, you can see what the boundary of this is. Okay, but it only contains part of the boundary, right? See this solid curve here? I'm indicating that's part of the set. This dashed curve here is not part of the set here, but it does designate part of the boundary, okay? And then the lines here mean I'm taking the interior here. I claim this set is neither open nor closed, right? Well, does this contain, let's start out this way. Is it open? Is it true that what? Every point is interior point? Well, no. See? I've got what? Boundary points included over here in my set, like right there, and this point here, and this point here. This isn't open. Okay? Is it closed? Well, does it contain all of its boundary points? No, there's boundary points over here too, right? That are not contained in the set. They're not part of the set. Okay? It's not closed either. What is it? Well, it's neither. It's neither open nor closed. Most sets in the plane are neither open nor closed. Okay? So the open and closed sets together are not exhaustive. Okay? A little exercise for you here. The complement of any closed set. You know what I mean by complement? The complement of any closed set is open. The complement of any open set is closed. What does it mean to be a complement? Okay? If S is a subset of R squared, okay, its complement, sometimes written this way or sometimes people write it this way, okay, is a set of all points in the plane R squared which are not contained in S, okay? So it's the entire plane except for the points of S. That's what the complement is, okay? Alrighty, so consider that. I'm introducing this to talk about the different ways people think about and define things involving limits here. Limits at boundary points of the domain of a function of two variables is what I'm interested in here. Okay, let's take an example. The limit as xy approaches 0, 0. The sine of xy over xy. I might have done this one the other day. What is the domain of this function? Okay, well, this function is going to make sense everywhere except where the product xy is 0, right? Okay, so this is the set of all points xy such that xy is not 0. Where is xy equal to 0? Well, xy is equal to 0 on what? The x-axis and on the y-axis. Everywhere else, you stay away from those points on the x and y-axis, and you've got what? You've got a function existing there, right? Okay, alrighty. Is the domain of this function open or closed? Think about it. Is the domain of this function open or closed? Look at the set here. Okay. Did you say open? Okay, you're right. All right. All right, here's what some people do with the definition when you're going like this. You're taking the limit as x and y approaches 0, 0. Okay, remember our definition for the limit of a two-variable function here. Okay. Some people make, in defining the limit, you do not have to consider that the function doesn't exist here at 0, 0, or what, along these two coordinate axes. Okay, when you're coming in here and you're approaching, you know, you should get the same value regardless of what you approach. So some people would write it this way explicitly. Just replace, say, call x, y, z and replace x, y by z. So you're taking the limit as z equals 0. Here we just put in that proviso x, y is not 0. Sine z over z equals 1. So they would still say that the limit exists. Okay? Alrighty, just to let you know here how some people do things. Other people might not like this and say, no, the function has to exist in an open disk at the point at which you're taking the limit. Okay? It's not true that this function even exists in any open disk centered at 0, 0, right? It doesn't even exist there. There's parts where it doesn't exist. Okay, so it all depends on different people's definitions there. Okay, this one's easier. Let's look at this function, sine of x squared plus y squared divided by x squared plus y squared. The only place where x squared plus y squared doesn't exist is at the origin. So the domain is all real numbers except the origin. Okay, by the way, is this domain open or closed, or neither? Okay. Do you remember that a single point is closed? Okay, it is closed. And when I take that out, take that away from r squared, I'm taking a complement. So this must be what? Open. Okay, this must be an open set. Once again. Okay. Now, since I'm going to take the limit as xy is approaching the origin of sine x squared plus y squared over x squared plus y squared, okay, I could just go the limit is z equals 0 of the sine z over z, which is 1, and not have any worries at all, because what? The only place where in this case it doesn't exist is at the origin itself. You're not having the problem that what? There's a whole big set of points different from the point of interest where the function doesn't exist. Okay, within open disk centered there. Okay, so different people will approach this slightly differently. Okay, this one is good with everybody. Okay, this one's good with everybody. Yeah, I'm just trying to make a smiley face here. Okay, some other people don't like this one here, precisely because of this situation here. Okay, but in our context, I'm going to go ahead and just say this does exist, okay, and is equal to 1. Okay, let me throw in here, I said topology of the plane. You can also do all this topology in 3 space, or in theory 4 space, 5 space, whatever. Okay, but here in 3 space we talk about, instead of open disks, we talk about an open ball centered at a point. This would be the set of all points whose distance from P is strictly less than whatever the radius of this ball is. Okay, so this does not include the surface of the sphere. It's a little sphere, but you're not including the surface of the sphere. Okay, the center of the sphere is the point P, but you're including what we would call the interior of the sphere, but not its boundary, not the very surface edge. Okay, so what's inside it, but not its boundary. This is what we would call an open ball. Okay, and when people start talking about topology in general, where you don't know the number of dimensions you're dealing with or anything like that, it's just completely abstract, and generally they just speak of open balls. Okay, so the topology is defined by open balls. Anyways, so you can do all this same type of thing in 3 space. Okay, now this was kind of ugly. I had to scratch out a couple things here. I wanted to show you this. Show that the limit as xyz approaches the origin in 3 space of xy over x squared plus y squared plus z squared does not exist. Okay, so what I did was go ahead and just parameterize a line through the origin. Okay, so that looks like I. That's really supposed to be 1. So here's a parameterized line. I'm using arc length as parameter. So I've got a u hat here, right? u1, u2, u3 is the direction vector. Okay, so you can see what the parameterized line would be. Y, or x equals u1s, y equals u2s, z equals u3s. Okay, now going back up here and substituting in my formula here, writing everything in terms of s, xy over x squared plus y squared plus z squared would be what? u1 u2 s squared over what? u1 squared plus u2 squared plus u3 squared s squared. Okay? And this would be what? u1 u2 over what? u1 squared plus u2 squared plus u3 squared. This is actually 1. I don't know why I wrote that. Okay? Since that's supposed to be what? A unit vector here. So that's what? u1 u2. So this thing is equal to u1 u2. Now our problem with the limit existing is it's supposed to be it's not supposed to be affected by the way in which you approach the origin, right? Or whatever point you're finding your limit at. Okay? You see, this is not independent of the direction of approach. Okay, this could actually be drawn out. Okay, so that's really just u1, u2. This is not independent of your approach, right? This depends on which direction you're approaching the origin, the value of this thing in the limit, okay? So the limit does not exist, so there's D and E, okay? Alrighty, in the next section, we'll start talking about partial differentiation. I hope you understood that. We're not going to do tons with limits or the topology, but I just want you to have the general ideas down. Okay?